Gravitational field. The definition of gravitational field is space around a material body in which its gravitational pull can be experienced is called its gravitational field. For example, suppose a material body is kept here. This is a body and having mass m. So this body can attract any other body up to this range. Suppose up to this range means the space around this material body. So this would be the radius of this, like, or the distance. So it can be attract any of the body up to this distance. So this space around this material body up to which any other body can experience any attractive force or the gravitational force is called the gravitational field of this body. That means this field is called the gravitational field of this material body. Okay. Next we'll see intensity of gravitational field. Intensity of gravitational field will define by the force experienced by body at unit mass placed at any point, provided the presence of unit mass does not disturb the original gravitational field, is known as intensity of gravitational field of the body at that point. For example, just now as I explained to you, this is an object. Suppose the mass of this object is m, the material body is m1, and this is the gravitational field of this material body. Now suppose any other body will place here of suppose m2 mass. So this body will experience a gravitational force because of m1, and when we are placing this body m2 inside the gravitational field of this body, so that cannot be disturbed the means original you can say the original gravitational field of this m1. So in such case the force experienced by m2 due to m1 is called the intensity of gravitational field at this point. Suppose this is the point A, and at this point m2 mass, any object of mass m2 is kept here. So m2 is experienced, suppose any force F. In that situation we'll say the intensity at point A of body m1, the intensity of the gravitational force applied by body m1 at point A is F. So this F can be considered as the intensity of the gravitational field at point A. Okay. To understand it, now we'll see here. We have taken an material body, means a material body of mass m, capital M, and this is the gravitational field of this material body which is having mass capital M. Suppose any other body is placed here inside the gravitational field of this material body of mass m. The distance between the center of these two is x. This is placed at point P. So the force experienced by this object of mass m at point P can be given by the law of gravitation, the law of force of gravitation, in which the force F is given by gmm upon x square, where g is the universal gravitation constant, m is the mass of that material body, small m is the mass of the body placed inside the gravitational field of material body, and the x is the distance between the two bodies. So this is F equal to gmm upon x square. Now it is said in the definition, the force experienced by body of unit mass. So that means if m mass body is experienced this much force, that means the unit mass body can experience the force F upon m, that can experience the force F upon m. So that is P is equal to, means sorry, this is at point P, the force experienced by unit mass body is given by F upon M, and if we'll multiply here also GMM upon x square, and will divide here also small m, then M would be cancelled. The remaining will be Gm upon x square. So this is Gm upon x square. That means this is the intensity according to the definition of intensity, the force experienced by any unit mass placed at gravitational field of any material body without disturbing its original gravitational field is called the intensity of the gravitational field of that material body. So according to that definition, I is equal to F upon M, and that is equal to Gm upon x square. Now the intensity is a vector quantity. The intensity of gravitational field is vector quantity, and it can be given by written in vector form, that I vector that is equal to minus Gm upon x square. Gm upon x square would be the magnitude, and x naught, this means x cap, this is the unit vector towards the you can say the center of the material body. So that is minus Gm upon x square, and this is x that can be represent the direction of the intensity. Here negative sign is just means the negative sign shows that the gravitational intensity is of attractive nature, as we have seen in case of the gravitational force also. When we are writing this in the vector form, minus sign came, and that will indicate the gravitational force is always attractive in nature. So here also the intensity is indicating here that is negative, and it is in attractive nature. Now we'll see, as x increases, you can see that as x increases, that means the distance between the two bodies will increases, I will decrease, and when x is infinity, in such case I will be 0. So it means the intensity of gravitational field is 0 only at infinity distance from the body. Means if a body is placed inside the gravitational field of any other body, so if you keep the distance between them infinity, then only the intensity will be 0. Okay, so the intensity will be 0. The intensity of the gravitational field will be 0 at infinity. Now as we know, if a be the acceleration, we know that suppose a be the acceleration produced in the test mass. Test mass means the mass which we have taken here, the unit mass we are taken here for the testing of the intensity of the gravitational field, that can be considered as a test mass. So test mass due to the force F, then force means if the A is the acceleration produced on the test mass, so in such situation the gravitational force or the force that produce acceleration on the body of mass m will be equal to ma, and acceleration will be equal to F upon m. But just now as we have defined the intensity as F upon m, that means that F upon m will give us intensity as well as it is acceleration. So simply or as the magnitude wise we can say that the intensity is equal to acceleration. It means that the intensity of the gravitational field at a point in the gravitational field is equal to the acceleration of the test mass placed at that point. And suppose if A is equal to, because this is acceleration, and suppose the body which we have taken is the earth, in such situation it would be what? It is I is equal to G, because G is the acceleration due to gravity, that means G is because of the earth's gravitational field. Okay, so I can be also written as I is equal to G in case of earth. Okay, now the dimension formula, if we'll discuss the dimension formula, we'll see here that is force, the dimension formula force is mlt minus 1, and this is mlt minus 2 here. The dimension formula force is mlt minus 2, and this is m, so m would be cancelled. It is m0 lt minus 2, m0 lt minus 2. Okay, now we'll see here SI unit, that is written as Newton per kg or meter per second square. Now the CGS unit, if we'll discuss, that is dyne per kg, sorry, dyne per gram or centimeter per second square. Now we'll discuss about the intensity of gravitational field at a point inside a hollow spherical shell. So this will be 0, hollow spherical shell. We'll see here, as we have discussed before also. Suppose this is a spherical shell of thickness, some thickness, this type of thickness, that means it is a hollow spherical shell. So if any point mass object is kept outside the body, means outside the spherical shell, so this spherical shell is considered as the mass of the spherical shell is suppose m, and the mass of that point body is suppose m. So this whole mass of this spherical shell is assumed to be concentrated at the center, and that can be dealt as the point mass. So the gravitational force between these two, the gravitational force between these two can be given by gmm, and suppose r is the distance between them, so it is r square. So gravitational force would be gmm upon r square. Now if in the spherical shell, this is the spherical shell, and now in this point size object is kept inside of the spherical shell. In such situation, here in the spherical shell, that uniform distribution of masses would be there, and each and every mass will apply the force on this. So for each and every mass there will be an opposite force will be there. For example, you can see that suppose this is the force, so this would be the force. So this way you will find that the each and every mass, means this can be understood very well by this way. Suppose we will take that the point mass at the center of the spherical shell, at the center of the spherical shell, that would be also considered as the inside the spherical shell. So for this mass which is here, and for this mass the force would be equal and opposite, and that can be cancelled out. So for each force there would be equal and opposite force present inside the spherical shell, and that can be cancelled all the forces, and so that the force inside, the gravitational force inside the spherical shell will be 0. Okay, now the gravitational force inside the spherical shell will be 0. So in such situation the intensity, because F upon m it is, that would be also 0. And here you will be you can see that in this case, that is F is constant here, means it depends on the distance between them only. Okay, so in such situation you will find that the intensity would have some value. It depends on the distance between them. Okay, but you know that as we increase, because F is inversely proportional of r square, as we increase r, F would reduce, because F would reduce, so I will be also reducing. Okay, so I also will reduce here. That means with the distance, with the increase of the distance, the gravitational force will reduce, and so that the intensity also will reduce. Then that can be represented here with the graph here, that is for a spherical shell or for hollow sphere. You can see that here we are representing the distance, that is r. Okay, and in y-axis intensity, or you can say acceleration due to gravity. So just now as we have seen, this is the radius. Suppose r, this much is the radius of the spherical shell. So inside the spherical shell intensity would be 0, and on the surface of the spherical shell intensity is maximum. Then outside the spherical shell the intensity will gradually decrease exponentially, as it is directly proportional to 1 upon r square. Okay, now for the solid we can say the intensity in like earth. if we are talking like Earth. Okay, so as we have seen the acceleration due to gravity g, the variation of the acceleration due to gravity g inside Earth and outside Earth and on the surface of Earth. So what we found there, we found that the gravity acceleration due to gravity would be maximum on the surface of the Earth. So here you will find intensity is also maximum on the surface of the solid body, solid sphere. Okay, and inside sphere you will see from center to the radius of the solid spherical body, the intensity will gradually increase. Okay, and it is directly proportional to r. But outside the solid sphere, the intensity will reduce, and it will reduce exponentially as it is reducing outside the spherical shell. So this can be given by this graph. This is for the hollow sphere, this graph is for the hollow sphere, and this one is for the solid sphere. Okay, so this is the variation of the intensity in the spherical shell as well as the solid sphere. Gravitational potential. Definition of gravitational potential is: gravitational potential at a point in a gravitational field of a body is defined as the amount of work done in bringing a body of unit mass from infinity to that point without acceleration. So we can understand this definition here. Suppose this is an object of mass m and it is kept at any point A. So, and we'll see here this is any other object of mass m, and this point P is in the gravitational field of this object. So suppose we have to bring this object from infinity to point P. So whatever work would be there, means whatever work we have to do to place this object from infinity to P, but the condition is that the mass of this object must be unit. The mass of this object must be unit. So suppose a unit mass of object is placed at infinity and we are bringing that object from infinity to point P, and P is the point in the gravitational field of this object. So the work done to bring this object from infinity to point P is called the gravitational potential at point P. The gravitational potential at point P. Okay. Now we'll consider if W is the amount of work done in bringing a body of mass m from infinity to a point P in the gravitational field without acceleration. Without acceleration. So in that case we'll say the gravitational potential must be what? It is W upon m, because it is the gravitational potential is the work done to bring a unit mass of the object from infinity to a point in the gravitational field. Okay, so we are bringing m mass of the object, so the gravitational potential would be work done upon m. And obviously it is a scalar quantity. The SI unit is joule per kg, CGS unit is earth per gram, and dimension formula is given by W upon m. W, the work done. The dimension formula of work done is ml2 t minus 2, and for mass m here, so m would be cancelled. It would be m0 L2 t minus 2. Now to find out the expression for gravitational potential at a point. To understand this, we'll take here, let Earth be a perfect sphere of radius r. The Earth is perfect sphere of radius r. So this is the radius of the Earth and the mass of the Earth is m here. So radius r and mass m. Now the mass of the Earth can be supposed to be concentrated at its center O. Now we'll calculate the gravitational potential at point P, and where the point P, this O P is equal to R, and this R is obviously greater than this R, the radius of the earth. OA, will see here, OA, this point is X, and AB is dx. So we are bringing an object of unit mass from point A to B. So whatever work we have to do to place the object from A to B, that work, if we'll integrate for infinity to R, will get the total work done to bring the object from infinity to point P, and that work done would be equal to the gravitational potential. So first of all, we'll calculate the work done to bring the object from point A to B. This is the distance dx. So the gravitational force of attraction on a body of unit mass at point A, and that is F equal to gm, because for unit mass it is, so in place of mass we'll write here 1. So gm into 1 upon x square. Now you will see that this is equal to gm upon x square. And suppose the small amount of work done in bringing the body of unit mass without acceleration through a small distance AB. So for this distance, the work done must be given by force into displacement. So because it is a small work done, so we are writing here with dw is equal to f dx. Now f is gm upon x square, and dx here is the distance between A and B. Now this is equation 1. Now we'll calculate total work done in bringing the body of unit mass from infinity to point P, and can be obtained by integrating this equation, the equation 1, within limit from infinity to R. That means when x is equal to infinity to x equal to R. So we'll just write the formula here, that is work done is given here by integrating gm upon x square dx within limit infinity to R. Gm, the universal gravitational constant, mass of the earth, these two are the constant quantity, and that will be come out from this integration sign. So we'll take the integration of 1 upon x square. So 1 upon x square, the integration of this will be equal to x minus 1 upon minus 1. This minus sign will come out here, and the x minus 1 is 1 upon x here. And we'll place the limit. This is infinity is lower limit and R is the upper limit here. So first of all, we'll put the upper limit minus lower limit in place of x. So minus gm, 1 upon upper limit is upper limit is R, so 1 upon R, and the lower limit is infinity, so 1 upon infinity. 1 upon infinity will be 0, so simply 1 upon R is multiplied with gm, so W is equal to minus gm upon R. This is the work done to bring the unit mass from infinity to a point P in the gravitational field of Earth, that is equal to W equal to minus gm upon R, and this work done is the measure of the gravitational potential at point P. So we'll write potential at point P. Potential we are representing with letter V here, and potential at point P is equal to W, the work done, and given as minus gm upon R. Now when R is equal to infinity, obviously Vp is equal to 0. The potential would be 0, and here because potential all the time the potential would be negative, but here it is 0, that means it will be the maximum potential at infinity. The maximum potential at infinity, because it is means 0, that means it is not negative, so that is the maximum potential. And when R is equal to R, that means when object is placed on the surface of the earth, in that case the potential is given as minus gm upon R, and that is at the surface of earth. Now we'll see gravitational potential energy. And gravitational potential energy is defined as gravitational potential energy of a body at a point in a gravitational field of another body is defined as the amount of work done in bringing the given body from infinity to that point without acceleration. The difference in the gravitation potential and potential energy. Gravitation potential energy. The only difference is that in gravitational potential, we are bringing a unit mass of object, a unit mass of body from infinity to the gravitational field, to a point of gravitational field. Here, in case of gravitational potential energy, we are bringing any mass of the body, means any body of mass m other than unit. Okay, so we are bringing the any body from the infinity to a point at the gravitational field, in the gravitational field. So for that, we'll simply see the previous figure only, and in previous figure as it is given here, this is the earth, and we are assuming the earth as a perfect square of radius r and mass m, and the mass m of the earth can be supposed to be concentrated at its center O, and to calculate the potential energy, we'll assume that potential energy at point P. First of all, we'll assume that at point A, any body of mass m is kept here, and that body is displaced from A to B. So whatever work is done to displace it from A to B is calculated first, and that can be integrated from infinity to r, and that will give us the potential energy. So as I told you, once again you have to understand the gravitation potential. In gravitational potential, we are bringing unit mass of means a body of unit mass, and here we are bringing a body of m mass, that means other than unit. Okay, then rest of the derivation is same only. The gravitational force of attraction on a body at A is considered as F equal to gmm upon x square, just applying the Newton's gravitational law. So this is gmm upon x square, where the x square is the distance between both the bodies, earth and the body. Now a small amount of work done to bring it from A to B, so that is equal to force into displacement. Because it is a small amount, we have written here dw, and it is equal to force into displacement. The force is what? gmm upon x square and dx here. Now total work done in bringing infinity, in bringing the body, means from infinity to r. So we'll integrate this small work done from infinity to r, gmm upon x square dx. So we'll get the same way, minus gm upon r as we have previously done. Only the difference is there. Here m will be multiplied the mass of the body which we are shifting from infinity to r, that will be multiplied here. Now since work done is stored in the body as its gravitational potential energy, so gravitational potential energy is represented with letter u, and u is equal to minus gmm upon r. Now u is equal to what? Minus gm upon r is the gravitation potential, and m is the mass of the body. So gravitational potential energy is equal to gravitational potential into mass of the body. One more thing is there here, as you can see the negative sign is there. So sorry, this minus gmr is the is equal to vp. So negative sign is here, that show the potential energy is due to attractive gravitational force. Now in this formula, if you see, if r is equal to infinity, u is equal to 0, and u is equal to 0, that is only positive value, and that should be maximum here. Now this formula, if we'll change the change in potential energy, that means when we are shifting the body till r1, or when we are shifting the body till r2, or we are shifting the body from r1 to r2. So the same formula will integrate from r1 to r2 within limit r1 and r2. So here the formula will come, that is gmm, that is 1 upon r1 minus 1 upon r2, where what? r1 is greater than r2. That means we are bringing the body from r1 to r2. We are bringing the body closer to the closer to the earth. So as the body is brought closer to the earth, its potential energy decreases. Why it is decreases? Because it become more negative. So as it become more negative, that means the lesser value will be there, that means the potential energy will decrease. So once again, when we are bringing or we brought any body closer to the earth, its potential energy decreases.